Good afternoon, and welcome to today's electronic design webcast. Our topic today is reducing costly downtime. Accelerometers transform machine maintenance, sponsored by TTI and TE Connectivity. I'm James Mora, Senior Staff Writer at Electronic Design, part of Informa's Design, Engineering, and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many as possible during the Q&A session following the main presentation, but please feel free to send your questions in at any time. To do so, simply type your questions into the window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now let's meet today's speakers. Bjorn Ryden is a Senior Product Manager of Vibration and Force Sensors at TE Connectivity and has over 20 years of experience in the sensor industry. He worked at Amatec Aerospace for over 8 years as a senior design engineer, where he designed critical sensors for the aerospace industry. Prior to joining TE Connectivity, he also worked as a senior applications engineer and product manager at Magit Sensors. At TE Connectivity for the past 12 years, he has held roles of increasing responsibility within the product management team. He holds a BS in Mechanical Engineering from Worcester Polytechnic Institute in Massachusetts. Ed Bacha, TTI's IoT Technical Marketing Manager, has over 31 years in the electronics industry. Before joining TTI in 2017, Ed spent 13 years with Avnet, serving in a variety of technical roles, including Technical Marketing Engineer, Business Development Manager, Regional Technical Manager directing FAEs, and spent 7 years as a Senior Field Application Engineer. Ed holds a BS in Electrical Engineering from Texas A&M University. Pete Smith is the Senior Manager, Sensor Product Knowledge and Training at TE Connectivity Sensor Solutions. With 47 years of experience in the design, manufacturing, and sales of high-tech consumer and industrial products, Pete has wide-ranging expertise in all aspects of product development, training, and engineering. For the last 32 years at TE, Pete has worked exclusively in the sensor space. His professional expertise in sensor applications includes an in-depth understanding of how various sensors enable successful customer designs. In his current role, Pete serves as a TE subject matter expert, sharing his in-depth sensor knowledge with colleagues, customers, and various external groups. Now let me turn things over to our presenters. Gentlemen, the floor is yours.
Okay, so in this section, let's review the current organizational challenges in the condition monitoring market. So if we look at machine downtime is one of the biggest issues in affecting factories today. The average downtime can last up to 4 hours, and which costs up to $1 million per incident. And typically the downtime is associated with a hardware malfunction. It would be a critical piece of machinery that stops functioning and requires a shutdown of the industrial production line. What we're seeing today is typical condition monitoring applications in the past have focused on very expensive machinery, where it would be costly. Downtime could cost millions of dollars to replace the equipment, and you typically would associate that with some big power generation equipment, turbines, where it was necessary to monitor these costly machineries in order to prevent downtime. What's happening now today is we're seeing a digital transformation in factories. As you're well aware, a lot of factories are going digital. They're becoming much more autonomous. There's less people in the factories. So there's a need to monitor a much wider range of equipment than was previously necessary. And to do that, it requires lot more sensors to be installed on the factory floor. Basically any reciprocating or rotating equipment now will require sensors to continuously monitor the equipment for predictive analytics and to improve the efficiency and lower the overall cost of the factory. If we look at a case study here, we're going to present a typical case study that requires the usage of these new embedded sensors. So for this particular application, it is a customer that has a large sorting warehouse for shipments, and they have a very large facility that has high volume conveyor belts. And in this particular facility, the downtime for them for the conveyor belts to stop working costs $10,000 per minute. So the customer requirements were they cannot afford downtime, any downtime. They want the equipment to continue to run 24/7. Cost per sensor is obviously critical because you're now installing a wide range of sensors over any reciprocating equipment. And for this particular facility, it requires up to 20,000 sensors to be installed. Wide bandwidth is critical. Some of this equipment, some of these spindles can rotate at a high RPMs, so you do need sensors that can measure wide bandwidth. Obviously, long-term stability. You need sensors that are very stable over time. You cannot afford any drift. Any drift can result in basically a false positive indication. And the customer itself did not have a technology preference, so they were looking at both the traditional piezoelectric sensors and some of the newer MEMS sensors. And good signal resolution is critical. If you can imagine, the spindles the amplitude deviations in the machinery requires such that you measure very low amplitudes in order to be able to earlier predict the downtime event. So the solution that TE presented here is our new embedded TE accelerometers. And the reason we presented this TE accelerometers was for a variety of reasons. One being wide bandwidth. There is no technology today that can compete with piezoelectric sensors for wide bandwidth. And this particular solution offers sensors up to 10 kilohertz. And also, it needs a high-performance health monitoring solution for virtually any speed equipment. Piezoelectric sensors not only covers wide bandwidth, but can also cover all the way down to 1 hertz. So you get basically a full spectrum of frequency response. Long-term stability is a key factor again. Piezoelectric crystals offers the best long-term stability on the market, far superior to MEMS sensors. They have a history of over 20 years in similar applications, and just the inherent nature of piezoelectric crystals gives you a long-term stability with no drift over time. They can also withstand wide temperature ranges from -40 to 125 degrees C if some installations require outdoor usage. Dynamic range, as I mentioned, piezo technology offers significantly better signal resolution than DC MEMS sensors today. You can typically get up to above 100 dB in dynamic range for piezoelectric sensors, whereas a DC MEMS sensor will struggle to even get to 70 dB range. And assembly is also critical. Depending on the application and how the customer wants to package the sensor, you may look at a stud mount unit, maybe looking at an epoxy mount unit, or even an SMT mount unit. So TE offers a wide range of solutions there. We have TO5 CAN configurations, we have stud mounts, and we have the new miniature surface mount devices in the 820M1. We also have single and triaxial solutions. So depending on which machinery is being monitored, it may be necessary to monitor biaxial or triaxial measurements as opposed just to a single axis. Okay, So now Pete's going to review some of the suited applications for these sensors.
Okay, thank you, Bjorn. As Bjorn mentioned, we have a wide variety of sensor products, particularly in the accelerometer area, and they find their way into a very large number of applications, and we're going to highlight a few of those here. One of the areas where people are looking to reduce their expenses and costs is in asset monitoring. You find this in warehouses and in stock storage locations where they need to monitor the various materials and components that they use in manufacturing facilities. They like to know if any of these, during the transportation of these products in the warehouse and from a supplier to a warehouse's location, if there's been any damage or any incidents that might create damage in one case or another. And using accelerometers in that case, they actually will affix accelerometers to shipments of products that are moving around, and they will include a data logger so that they're collecting data on a continuous basis. And as the products move on a truck, for example, from one location to another, or within a particular warehouse on a forklift from one location to another, if an incident occurs where there's a shock or a bump or something that is of significant amplitude to create or cause damage to the materials or the products, they record that. And then they can review it later if they find that some of the products are not working as they should in the production process. These kinds of applications also are used for tamper detection. When you put a sensor on here, you can detect when it moves. And if it's an unauthorized move, you can notify a security feature somewhere in your warehouse and say, hey, somebody's taking these or moving them in a way that you don't want that. We monitor, again, for drops and impact damage. And these are particularly useful in high-value asset tracking. And they will adapt to blockchain. We aren't seeing much blockchain implementation yet, but it's probably coming. And these sensors will be used as input nodes for blockchain data. We also see applications for these accelerometers in rail health monitoring. There are various very complicated mechanical devices on typical rail. The one pictured here is an electric rail system that has electric motors, drive systems that are underneath the cars with wheels, a lot of bearings, a lot of mechanical activities going on under there. And to make sure it's all operating properly, the addition of accelerometers can help a lot with identifying problems that may happen in the future if they go into the rail trucks, into the tracks in the roadbed, and in maintenance with their maintenance equipment. And for magnetic levitation trains, I believe that some of those are actually in operation in various parts of the world, and they're being installed more and more. The accelerometers can monitor the actual levitation space above the rail bed. And it's very important that that be maintained at a critical level so that the train can travel at the very high speeds. The use of the accelerometers in these cases can provide predictive data that can actually, the operator can actually determine if a bearing, for example, or a motor is going to fail in the near future. They might be able to listen to a bearing and any acoustic noise that it's making with an accelerometer and say that this bearing is going to fail within the next 100 hours of operation. And then they can schedule downtime for that particular rail car, put it in a maintenance shop, and change the bearing or repair it or do whatever they need to do so they can put the car back in service. By scheduling this maintenance, they save a lot of problems so that the car doesn't fail while it's in transportation on a track somewhere, and then can shut down the rail line. So this is a huge cost savings for these kinds of operations. Our accelerometers are also used in impact testing, sport helmets. As you know, there's quite a bit of talk lately, particularly about in professional football circles, about the need to improve the protection, the gear that the football players are wearing so that they don't get these serious brain injuries that can accumulate over time. And so in the development of those kind of products, they affix a lot of accelerometers to the testing equipment and the development equipment so they can monitor carefully the shocks and impacts that you might see. In some cases, there's even talk of putting accelerometers directly in helmets for real-time monitoring, and during plays on the field, they can actually monitor the impact at a particular player, and if it exceeds a certain threshold, they might pull the player from the game to check him out from the medical team. These kind of things are also being used by the military to monitor soldier activity. Sadly, soldiers are in battle sometimes, and they can be affected by explosions or munitions that are going off close by and creating shock waves that can actually cause injury or damage to the soldiers, to their head or brain or whatever body part that might get exposed to the shock waves that come from that. And so they can monitor those kind of events with accelerometers in their clothing, in their helmets, and in the gear that they wear, the vests. Aircraft seat ejection and blast detection are also places where these accelerometers are commonly used. Some more examples. The one that Bjorn mentioned before is vibration monitoring that's used in factory settings. In the case of the conveyors that he was mentioning, you find the sensors to determine that the conveyors are operating properly and can flag a particular conveyor portion that may have some problems coming up, and they can do some maintenance on them. You also find these accelerometers being used in electric motors and drive systems for equipment all over factories. As you might expect in a manufacturing facility, every machine's got electric motors in it, and the electric motors have bearings, and you can monitor the health of that motor simply by listening to it. They have very standard acoustic signatures that will signal a healthy motor. And as the motor starts to develop problems, those acoustic signatures change, and we can actually listen to those events with our accelerometer products. Machine tools have the same artifacts going on there, and the data from these accelerometers can feed into smart factory systems. It can go into the cloud where analytics are done, and then they can get reports that explain that there are some areas of the factory that they need to plan some maintenance. Wind turbines is another area where it's very important. One of the problems in wind turbines is that if you get a catastrophic failure, it's a very dangerous situation. These wind turbines, if they fail spectacularly. They have blades flying through the air, causing problems. They have fires, electrical shorts. It can be a very dangerous situation. And so they like to do predictive maintenance on these so they can get in and fix problems before they actually turn into a catastrophic event. They monitor the bearings. There's bearings in the hubs. There's a lot of generating equipment in that pod that exists on top of the stanchion there. And they want to make sure all that's working properly. The blades are actually wings that are flying through the air, and typical of any kind of a blade that's flying through the air, you get flutter problems and resonant frequency issues that you need to monitor. And in some cases, if the resonant frequency flutter gets out of control, you can actually break these blades. So they monitor the possibility of flutter, and then they can change the pitch on the blade as it's running to avoid flutter situations. And so the accelerometers are used in real time to prevent problems or failures in the blade systems on these things. Out of balance is easy to detect too, because if anything goes out of balance, the bearings aren't designed to handle that situation and can fail very quickly. We use our accelerometers in structural monitoring too, bridges, buildings, tunnels. We listen for a couple of things there. First of all, seismic activity. It shows here the Golden Gate Bridge. As you might expect, it's in earthquake country in Northern California, and they're very sensitive to the effects that earthquakes have on structures like this. So they like to put sensors all over them. Caltrans is the local agency that actually heads this up, and they are outfitting many of our structures with accelerometers and vibration sensor monitoring so that they can determine in an earthquake event if there's any need to send in technical people to inspect the bridge or the tunnel abutments or any of the things that are going on highways to determine that they haven't been overstressed and they're still safe to use. Wind loading and dynamic road vibrations are always issues on bridges and things like this. So again, it's all aimed at, in this case, at creating safety situations for the public, and it's a very good use of our accelerometer products. Okay, I'll pass it on to Ed.
Thanks, Pete. The purpose of this slide is to show that TE has many fantastic products from multiple divisions. Now, many devices can be used in one application, and you can have multiple TE devices from different divisions in one application. So in this particular example, this is a remote IoT vibration monitor, and it's wirelessly connected to the internet. Starting from the top left of the page and moving counterclockwise, we see that the first device is an antenna. This embedded antenna from TE has dual band capability for both Wi-Fi and Bluetooth, and it supports the 2.4 and 5 gigahertz frequencies. This antenna is constructed using traces on a PCB board and is only 1.57 inches wide. It has an adhesive tape backing to affix it to the internal surface of the enclosure for greater signal sensitivity and better transmit power than a surface mount antenna. It's available with 3 different connector options and has a peak gain of 3.7 dBi. The next component, this TE832M1, is a surface mount accelerometer that's very similar to the one that's been profiled in this presentation. Now, TE has many different types of accelerometers, some in ruggedized packages with a cable, so you can mount it directly to the interior surface of the enclosure rather than on a board. Also, it's available in multiple sensitivities from plus and minus 25, 50, 100, 200, and 500 G. Now, as the shock and vibration increases in different applications, the G forces increase, and that's why there's a need for multiple ranges, depending on the application. Now, all of these applications are unique, and they're going to need a different option and a different type of accelerometer. The next component is a sensor that measures pressure, temperature, and humidity, all in one device. The MS8607 is very popular because it's in a very small package, and it's basically 3 sensors in one, and it comes fully calibrated from the factory. You won't see many PTH sensors from other suppliers because it's difficult to build, but TE has the design expertise and the packaging technology to accomplish this. The temperature range on this device is minus 40 to plus 85 degrees C, so it'll fit most industrial applications. This combination sensor is accurate enough for HVAC and even weather station applications. So with the pressure, the temperature, and the humidity, you get a perfect device to monitor the conditions in and slightly outside the enclosure. Now, moving to the upper right-hand corner of the page, you'll see the TE battery holders. Most IoT sensors are remotely deployed and run on some form of battery, and you'll need to connect that battery to the board or to the enclosure. And TE has many options for battery holders and DC contacts for a variety of applications. TE has a solution for you, and you can contact a TTI sales specialist for assistance in selecting the right option for your design for all of your components. Now, these aren't the only devices in a typical application like this, and later in this presentation, we'll go through some of them. TE has flow sensors for liquids. They have force sensors, position sensors, and speed sensors. And there's even a water level sensor, just to name a few. Many of these are designed for industrial applications, and some of these have threaded pipe interfaces with cables or a connector where you can connect these devices directly to the industrial application. Okay, Pete, back to you.
TE Connectivity has been at the business of providing these capabilities to our customers for a very long time, over 75 years. We've been a leader in the connectivity world, and there's some, TE Connectivity have been created from a conglomeration of earlier acquisitions, consolidations, a few divestitures. To the company that we are today, there's some names in our history that you might recognize. AMP was a connector company primarily about 20, 25 years ago. Deutsch Raychem is a chemical company that excels in polymers and shrink tubing kind of applications. Pergana Medical did interventional products for the medical industry. Interconnect, we also acquired Measurement Specialties 4 years ago that brings our sensor technologies into the fold here. But one of the overarching features of all of these acquisitions has been the ability of the products to survive harsh environments. Most of our products are designed with that in mind. And so what is a harsh environment? Essentially, the sensors, those connectors are designed to withstand exposure to high temperatures, very low temperatures, wet environments where the humidity is very high, or in some cases, the products are operated underwater. We make waterproof devices. Where there's levels of high vibration or impact. As you might expect, as pictured here in the robotics arena, those things are moving around a lot. There's a lot of vibration, there's shocks, there's impacts. We have to make our sensors capable of withstanding these kinds of environments. And we do a very good job at that. As I said before, the largest number of our products are designed to withstand this kind of environment. We also offer a wide variety of other sensor products, and we'll discuss a few of those here in a few minutes. But we offer photo-optic sensors, we offer position sensors, fluid property, sensors that are based on an interesting technology called piezo film. They can do things that you don't expect. We make humidity sensors, relative humidity sensors. We make pressure sensors, temperature sensors, force and vibration. And I think, as Ed mentioned before, liquid level sensors, if you want to measure the level of a liquid in a tank or a vessel or even a lake. We make sensors that are used in environmental monitoring where they monitor lake levels, sewage treatment facilities, all kinds of things. So we do have a wide variety of products, a wide variety of sensors, and we can handle any sensor need that you might have. We are a world leader in these products, as you can see by our wheel here that shows all of our various products. We are everywhere. We're one of those companies you may not have heard of us, but we are everywhere. We're in your automobile. We're in your appliances in your house. We're in your house in the air conditioning system or heating systems. We are in the commercial aircraft that you fly in. We're in your appliances. We're in your the UPS truck that brings your deliveries. We are there. And we're in the medical arena, so that when you go to the doctor, you interface with our sensors. You go to the hospital, and there are sensors that are taking care of you there. So we are a very big player. We offer a wide variety of products that go into a wide variety of applications.
So if we look at the portfolio of accelerometers, particularly for these applications, we have a whole range of options and solutions for the end user. We look at we come back to what we discussed earlier. Some of the features here, if we talk about wide bandwidth, so we have wide bandwidth measurements from 1 hertz to 10 kilohertz for our sensors. And basically it offers a single solution. So a customer can pick our sensors and install them both on low speed and high speed reciprocating machineries. So if there is one solution, one size fits all, we have that. And the customer won't need to buy different sensors for different machineries. We have one size that fits all. And another feature that's critical is the long-term stable output. There is no solution on the market right now for condition monitoring that offers a better long-term stability than piezoelectric technology. It is magnitudes better when it comes to long-term drift than DC MEMS. Another feature is superior dynamic range and resolution. If you want to be able to detect a failure mode early in order to prevent a catastrophic failure, the earlier you can predict that failure, the better. And in order to be able to predict the failure earlier, you need as wide dynamic range as possible, so you can measure small amplitude deviations. And in order to do that, piezoelectric technology, again, is superior, having over 100 dB of dynamic range. Some other features of our portfolio is we offer a couple of different output interfaces. We have the traditional IEPE, also known as ICP interface, which is a current excited 2-wire interface. But we also offer a 3-wire electrical interface, traditional for voltage input data acquisition interface. And really that depends on the customer's needs, what type of data acquisition and what type of PLCs they have for monitoring the equipment. In any case, we have both solutions for them depending on what needs they have. Finally, also features. Mounting can be critical in these applications, and depending on the type of machinery, the space allowed, the customer may decide on a TO5 epoxy mount, or we also have a TO5 stud mount sensors, or they can decide on miniature circuit board mountable units. Particularly the new 820M1 offers a miniature circuit board mountable configuration that can be installed in high volumes through traditional SMT processing. And we also have single and triaxial configurations of these. The 805, 805M1 are single axis TO5 configurations, but we do have triaxial configurations in the SMT design, such as the 832 and 832M1 for lower G applications. And as we mentioned, in some of the higher G, particularly sports explosive and helmet impact applications, you'd be looking at the 834, 834-1 series for those applications. Okay. And for other portfolios now, Pete Smith, we'll circle back to him to discuss some of the other related products.
Thank you, Bjorn. As we've alluded to a little bit during this presentation, TE makes a wide variety of sensor products, far beyond the accelerometers that we've talked about in detail here. We have a number of technologies that result in, again, a wide variety of products that are used in even a wider variety of applications. We we'll focus a little bit here on some of these other temperature sensing technologies that we have and pressure sensors that are used in machine health monitoring. We do make a line of temperature sensors that are specifically designed for machine health monitoring, and typically the temperature sensors are used in monitoring bearing operation. A properly operating bearing in a motor or some sort of mechanical piece of equipment will run at a very predictable temperature. As the bearing starts to wear and a failure is imminent, the operating temperatures of these bearings starts to increase. And so they look for that with this condition monitoring equipment. And as soon as they start to see a deviation in the temperature in terms of it getting hotter, they can say, okay, we got a problem with this bearing. We better schedule downtime and do some maintenance on it. So the temperature sensors, we make specific designs that are designed to be fitted directly to a bearing housing. We also make temperature sensors that go into industrial ovens and baking systems. You may find many ovens used in industry for curing adhesives and epoxies and paints. You also find temperature sensors in baking systems to monitor the heating elements, so to make sure you're not overcooking or undercooking food in a large processing facility. Chemical processes in oil refineries, for example, or chemical processing facilities, temperature in many of those processes is critical. And so to make sure the process is working at its highest efficiency, they monitor the temperatures very carefully. Also in food processing, particularly in beer and wine making, we've found that there's a very high use of temperature sensors in those operations, because the quality of the finished product relies greatly on the temperature of the processes that are used to make them. We also make a line of pressure sensors. Mostly these pressure sensors in this particular types of applications are used to monitor factory systems where you're providing compressed air, or you're compressing a liquid or pumping liquids around a factory to monitor the proper pressures in the systems and the right amount of liquid or fluid is flowing in the right direction to get to the right pieces of equipment. You can combine the pressure sensors with temperature sensors to measure hot and chilled water distribution. In a lot of factories, you have that kind of a thing. In high-rise buildings, a lot of times for air conditioning, they use chilled water that's chilled in a chiller on the roof, for example. Then they circulate that cold water through the building so they can, if that's not working properly, they can monitor it with the temperature sensors and pressure sensors to make sure that that system's working properly. And in many factories, you have vacuum systems that are distributed throughout the facility, because a lot of machinery out there requires a vacuum. And so you bring the vacuum system capability right to the machine from a central location, much as you would use distributed wiring or things like that, compressed air. So they monitor the condition of the vacuum system to make sure that it's adequate to keep machines running properly. We also make a line of speed sensors. Bjorn referred to this briefly earlier, that are designed for monitoring the speed of rotating machinery. These sensors operate either from Hall effect technology or variable reluctance sensors or eddy current sensors. We offer it in 3 different technologies. And they are designed to literally measure the speed of any particular piece of rotating equipment, gears in transmissions, for example, or a particular piece of rotating machinery that's in a factory that is used to assemble products. You want to know exactly how fast the machinery is operating. We also monitor the speed of turbochargers in engines with these particular sensors. To again, the output of the sensor provides the turbo speed to the engine control unit, and it can alert the system that if the turbine is not operating properly, if there's problems in the bearings, or if it's not achieving the right speeds and getting the right efficiency, because the efficiency of the engine and its ability to keep emissions under control relies on a number of parameters, and the turbocharger speed is one of those. So we provide sensors to monitor those kinds of parameters in various kinds of engines. And then we make position sensors. Our LVDT gauge head sensor products are designed to measure very accurately the position of particular machinery. If you have a machine that is assembling 2 pieces of work together, and the position of those to be located very accurately is important, we offer sensors that do that. They can tell you within down to microns in some cases that the pieces are located correctly, and then the machine can do its thing. It can apply a crimp or insert a rivet or do something to hold these pieces together. And we'll know
so a few of you have already
properly.
submitted
so
questions,
we monitor
so we're going to jump right in.
efficiency
if you'd like
and
to
the
submit a
accuracy
question,
of
type it into the
production
question window on the
processes
side of your
with these
screen and
kinds
hit
of
the submit
devices.
button. While we're answering your questions, please complete
Okay,
the feedback
questions.
form, which is located on the bottom of your screen. So the first question is, what mounting techniques and materials are recommended to achieve the best high-frequency response for the board mountable accelerators?
Okay, this is Bjorn Ryden. I'll answer this one. To mount the model 820, the board mountable devices, such as an 820M1, 832M1, we recommend you use standard solder reflow mounting and secure the unit during the reflow mounting just to make sure that it's mounted flat, parallel to the mounting surface. We also recommend for best transmissibility for higher frequencies to use a ceramic circuit board that has good TC matching with the LTCC carrier. It also is a stiffer material, so when you get into higher frequencies such as 3,000, 4,000, 5,000 hertz, you really want to get away from the FR4 circuit boards. Lower frequencies, down up to maybe 2,000 hertz, the FR4 boards are suitable, but at a minimum thickness of maybe 60 thousandths of an inch. I'll also add, after you've reflow soldered the devices onto the board, we typically recommend an underfill. There'll be a small gap between the sensor and the circuit board after normal reflow soldering, and we like to fill that gap so you get good transmissibility. And we recommend a cyanacrylate, probably a Loctite 451 might be a good suggestion, that is low viscosity, and you can fill the gap underneath the sensor and stiffen up the mounting.
So the next question is, if higher ranges are requested, can TE customize the sensor to higher than 100G?
The short answer is yes, and we already do it. So our standard 820M1 is designed for 25G, 50G, and 100G. Those are three of the most popular ranges for the applications targeted, but we can make these sensors up to 6,000G range. If you look at a model 834M1, that's a board mountable triax device, and those devices are available in standard catalog up to 6,000G, and a very similar construction to the 820M1. So if needed to have a higher G range, it's certainly not a problem.
The next question is, are these raw sensors, or do they contain any algorithms to process the vibration information? You can tie the accelerator to an ARM M0 processor, but isn't the secret sauce in deciding what is normal vibration and what is abnormal?
Okay. Pete, do you want me to take this one?
Yeah, go ahead. Go ahead,
Okay.
start, and I can make a couple of
All right.
comments too on that.
Okay, so yes, the question is correct. The sensors that we have shown in this presentation, they are small board mountable chips. So there is a piezoelectric ceramic PZT crystal inside, and then a charge converter. So you're getting a raw analog voltage output signal from the device. In order to determine what that signal means, you're going to have to do post-processing. And it really depends on what type of machinery and what you're monitoring that machinery. The intelligence needs to be in your data acquisition or your post-processing of the signal in order to determine what events to look for. So I will add this, however. We do have in our TE portfolio what we consider our smart condition monitoring transducers. These are much larger devices, So they're not SMT devices. They're fully packaged in a stainless steel housing with a connector. And we have designs in our portfolio where we include an onboard FPGA processor. And what that enables an end user to do is to add the intelligence onto the sensor itself, and you can program those sensors to look for the exact events or a range of events that you need in order to monitor, depending on the machinery that you're monitoring. And a new release coming out in the near future is a wireless version of those smart sensing devices. So look for that soon to come out. And if needed, we will have a fully packaged device with a onboard intelligence.
Yeah, Bjorn. I'd like to add a little bit. The part of the question was, how do you decide what the difference is between a normal vibration and an abnormal vibration? Sometimes the techniques that are used include a signature analysis algorithm. And what that entails is basically looking at, for example, an electric motor. You can attach the accelerometers to an electric motor, and essentially they become contact microphones, and they listen to the motor in operation. And a new motor will have a very specific acoustic signature that says that, yes, I'm running normally, and this is what I sound like. And so with use of these accelerometers and their ability to capture very accurately that acoustic signature and all the various strange little anomalies and bits and pieces that might be included in it, they record that information. And then as the motor proceeds in service over months, years, or however long it's going to be there, you continuously listen to it with those accelerometers. And at some point, when something starts to fail, a bearing starts to fail, or the windings aren't working right, or there's the brushes, if it's a brushed motor, are starting to wear out, the motor starts to make noises and sounds that are different from the initial acoustic signature that was recorded. And using some of the signal processing capabilities for many of the processors that are available now, you can actually begin to detect those anomalies, those fine little points where it doesn't quite sound right. So what they do is they listen for that, and they start to note it, and they use fuzzy logic. They use all kinds of software techniques to analyze these acoustic signatures. And when they finally decide that, okay, it's bad enough, the differences are bad enough or significant enough that the motor is going to fail at some point in the near future, then they alert the operator to say, hey, it's time to schedule some downtime and go either replace or do maintenance or fix this motor. So it's a lot of the, I guess, for a total system, a lot of the secret sauce in it resides in the software and the capabilities of the system to do digital signal processing.
So the next question is, we generally conformal coat our circuit boards to protect the circuitry. Would there be any concern with conformal coating?
No, we
Go ahead, Bjorn.
Go ahead.
No, go ahead, Bjorn.
No, we don't have any concerns with conformal coating. In fact, in some of our packaged devices, we do conformal coat in-house. The only concern with conformal coating is if you had a device that had exposed wire bonds or something like that. But all these units are full, all SMT devices, so we don't have any concerns with conformal coating.
And I can add something here too. There are some of our sensor products that conformal coating does create a problem if it's not applied properly. With conformal coats, with some of our sensors, they are actually designed to monitor the atmospheric conditions around, for example, a humidity sensor. If you completely conformally coat a humidity sensor, you seal it up so that the ambient humidity doesn't actually get to the sensing element inside. So it'll never be able to report accurately what the ambient humidity is. So in cases of sensors like that, some of our temperature sensors are like that too. If you add conformal coating to them, it changes the way they operate. It changes their time constants and their ability to monitor the local temperature, for example, particularly in the air. So it's important to recognize that every sensor, to operate properly, must be connected intimately to the phenomenon that you're trying to detect, trying to sense. And if you introduce a conformal coating, that actually isolates or insulates the sensor to some degree from the phenomenon that you're interested in. Some of our sensors, it's not a problem. As Bjorn pointed out, the accelerometers, there's no problem because we're monitoring vibration, which passes through conformal coating with no trouble at all. But some of our sensors, you need to approach those with caution in applying the conformal coats. I hope everybody understands that.
So the next question is, what other sensors can TE offer for a connected solution?
Wow. We've got lots. We have a whole array. We've got pressure sensors, temperature sensors. We have position sensors that can monitor both linear and translational motions, relative motion, absolute motion, rotary motion. We make rotary encoders and rotary motion sensors. We have force and load sensors that are used to measure anything from down to a few hundred grams up to 1 million pounds. And all of these sensor technologies can be made part of a health monitoring system for a factory. As you might expect, a large factory has a wide variety of manufacturing equipment and machines in it. All of them are candidates. We're working on a project right now internally on how to populate a plastic injection molding machine with sensors. And there's a wide variety of sensors that we're using on this thing. We're using accelerometers, we're using load cells, we're using pressure sensors, we're using temperature sensors. And it's all aimed at providing capability to make sure the machine is operating properly and to make sure that it doesn't catastrophically fail and create downtimes that cost a lot of money.
So the next question asks about the power consumption for an accelerometer.
Okay, so yeah, so the power consumption varies depending on the model you pick. We have, if you look at a typical 820M1, it's I should mention they're all very low power consumption. So if you look at a model 820M1, we're talking about 22 microamps current consumption. The lower, we have devices that have, an 832M1 uses the same circuit, so that's also 22 microamps per channel, being a Tri-X device. And then we have an ultra-low power device, which is the regular 832, not the M1 version, and that goes down to 4 microamps. I will say this, the caveat, when we go from the 22 microamps down to the 4 microamps per channel current consumption, you do give up on bandwidth. So if you look at a model 832, it'll only be up to I believe, 2,000, 3,000 hertz. If you need the 6, 7, 8,000 hertz bandwidth, then you have to go with the M1 version. So there's a little give and take there on the current consumption. Looking at the question here, there was a question in regards to wireless. So if we look at the question is in regard to Bluetooth. So as I mentioned, we are releasing a wireless version. It's not Bluetooth enabled, it's actually LoRa enabled. We can do a Bluetooth version too. We have a Bluetooth wireless sensors in pressure portfolio. If you were to design a wireless accelerometer using an internal 820M1 or a similar package device, an 805M1, and you were to send a signal out to the system, alert the system, let's say once an hour. Our typical, what we estimate for the battery life, then you're looking at about 5 years of battery life with the current battery technology available today. So just a rough estimate, once an hour sending the signal will give you 5 years of battery life. I hope that answers it.
So the next question, I'm going to put these next two together. So the first question is, how do you view data collected from the accelerometers? And the related question is, what type of data does the accelerometer collect? Does it not collect spectral data, just acoustic noise?
Bjorn, let's see. I'll take a shot at it, Bjorn, and then you jump in here.
Sure.
The data that our sensors primarily provides are signals, voltage signals. Sometimes we can provide them as current signals, and a few of our sensors are actually, the output is a resistance. But in the accelerometer area, it's primarily either charge or voltage are the fundamental signals that we get out of them. Bjorn, do we have some 4 to 20 milliamp accelerometers too?
We do have 4 to 20, but not in the embedded packages. So we have fully packaged devices that have 4 to 20 current output. Okay. In the packaged devices, in the embedded devices here, we have the 3-wire voltage, and we also have the IEPE, or another trade name, ICP, pack device, such as an 805.
Okay. But to view the data, most of our customers take those electronic signals, voltage, varying voltage, or currents, or whatever, or charge, and they make them inputs into data acquisition systems, typically. Sometimes they will perform transformations on them. They'll do an FFT, a fast Fourier transform, for example, convert it from time domain into frequency domain, because what they're more interested in is in the frequency domain. But our customers generally take the data. We're really good experts at the sensor part of it, and our customers then take the data and analyze it on their own to their application needs that they have in their equipment. So I think a lot of things happen to that data. Sometimes it gets stored. Sometimes they do analytics. As I said, they do transformations on it, and then they take that data and make determinations based on it. For the accelerometer, it does not collect spectral data, just acoustic noise. The answer is yes. That's kind of it. The spectral data, again, you have to do, as I said, you have to do an FFT to really look at the spectral part of it. We don't do FFTs in our accelerometers yet. But there's a day coming. You've probably heard of the term edge computing. That's where you're starting to put more intelligence out at the very edge of your systems. And one of those phenomenon that we'll be doing things like that in the future. We're already starting to put more intelligence in some of our sensors now. And although we don't offer them with spectral capabilities at this point, there's probably a day out there where we will.
Okay, so we have time for one more question. The last one will be, what's the difference between the variable capacitor vibration sensors and PE technology in predictive maintenance for condition monitoring? Okay.
I'll take this one. If you look at, for condition monitoring, there's 3 parameters that we consider critical. You have a wide range of machineries. They're located at different speeds. So having a device that has wide bandwidth is one of the critical parameters. And the second parameter that we consider important is dynamic range, or what we call resolution. The better the dynamic range and the better your resolution is, the earlier you are able to detect a problem with the machinery. If you can measure much lower events, you can actually predict the failure much earlier and then stop the machine from a catastrophic failure at a much earlier time. And finally, we also consider drift critical. These devices are installed on the machineries, 5, 10, 15 years. If your baseline signal starts to drift over time, then you could be getting a false positive eventually. Triggering a false positive is not due to the machine itself, it's the sensor itself drifting. So if we look at those 3 parameters and compare it, a VC versus PE device, A VC, variable capacitive MEMS device, is DC coupled. It's an ideal for static and low frequency motion measurements, not designed for high frequency measurements. In fact, there isn't, I don't know a VC sensor on the market that can do much over 2 kilohertz. They are great for static and low frequency measurements. They're not good for higher bandwidth measurements. And that's where PE has the advantage over VC. PE has been in the field for 30 plus years in condition monitoring, and you can get bandwidths up to 12, 15, 20 kilohertz on special occasions. If you look at dynamic range, again, PE has a big advantage over VC. You're looking at a dynamic range for a VC sensor at best maybe 80 dB. You're probably down in the 70s, 60s, depending on what device you're looking at. A typical PE sensor will have a dynamic range of over 110 dB. It's just a night and day difference in the resolution between the two devices. And finally, drift. Piezoelectric crystals themselves, they are inherently much more stable than a MEMS device. A MEMS device is always under stress and strain. It drifts over time. We have MEMS devices in our portfolio. We have piezoresistive, and we also have DC MEMS devices in our own portfolio. We just don't target condition monitoring with that technology. And the reason is, as I've mentioned, the wide bandwidth, the dynamic range, and the long-term stability. And hence why we choose the PE technology.
Well, that's all the time we have for today's questions. If your question was not answered, the presenters said that they would get back to you with answers. And that concludes today's presentation. On behalf of Electronic Design, I'd like to thank TTI and TE Connectivity for sponsoring today's event, and of course all of you for joining. Have a great rest of the day.